Hello and welcome to another video. In this video we're going to be doing the problems from Weekly Contest 396. And let's start with the first one. So the first one's pretty easy. You just are getting a word and it's valid if it contains a minimum of 3 characters and all these things. So the minimum of 3 characters, you can just check the length. It consists of all these things. So this is basically, it just needs to be an alphanumeric character word. There's a Python function to do that. You can also just use ASCII values to check for all these things. So just check for the ASCII value of upper and lower and numeric. You can also use lower and upper and stuff to make everything upper and lowercase to make it easier. And then it includes one vowel and a consonant, so you can just keep track of how many you have. And you just check if it's alphabetic, check if it's a vowel or a consonant, and just return if both those are true. So pretty easy one there. So for the second one, you have a word of size n, and you have an integer k, and k divides n. So the length of n mod k will be 0. And you're basically asked, you can perform this operation any number of times. So you can start at an index, any index you want, and you can take some chunk of length k and put it somewhere else. So in this first example, you have LeetCode Leet. So you're basically trying to make it so whenever you divide the word into chunks of length k, every chunk is the same. So you have 2 chunks here, or 3 chunks. So one chunk is leet, one chunk is code, one chunk is leet. And the basic thing here is you can basically just go through the word and divide it into chunks of length k and then get a count for each. And then you're just going to want to convert everything into the chunk that occurs most often. So in this LeetCode Leet, leet occurs twice and code appears once. So you just change everything into leet. So you just figure out how many chunks to have total, which is just length of the word over k, right here. And then you just go through every single value, the count of every chunk, and you see how much does it take to convert everything into that chunk, which is just the total minus the count of that chunk. So if I have 2 leets and 1 code, to convert everything into leet would be 3 minus 2. To convert everything into code would be 3 minus 1, and so on. So pretty easy one there. Then this one, so the main thing for this one to recognize, to make it not very hard, there's probably other ways to do it, but this is just how I did it, is, so you're given a string and it's a concatenation of anagrams. First you have to know what an anagram is. So an anagram just means a bunch of characters in any order, but the count of every single character has to be the same. So if you make a dictionary of letter counts, they have to be the same for anagrams. So here, if you make a dictionary of letter counts, they'll be the same. And you can divide your word up into anagrams of any size you want. And you want to return the length of the smallest anagram that you can use to divide your word into. So in this first example, the anagram would be A and B, so 1A, 1B, and that would be length 2. So AB is 1A, 1B, BA is 1A, 1B. In the second example, C, D, E, F, every character is unique, so the smallest anagram is just the whole word. So the main thing they recognize is actually what you need for an anagram to work. So one of the main things to know is if a word is length, k, the length of the anagram that you pick, call it L, has to be 0. Right? Because if I want to divide my word into anagrams, let's say my word's 500 characters, if I want to divide it into anagrams of length 8, my word has to actually be divisible by 8. So there's actually, for a big number, there's actually not that many factors of a number. If I just print all the factors of a million, there's not that many. I think there's 50 or something. So we can try, so we can say find range, let's just say a million or something. Or yeah. So we can say, I think a million will actually give me output limit exceeded or something. I was trying this earlier, but let's just try something like this. We can say if, and let's say our number is, so let's just say if 10 to the 5th mod I equals 0, print I or something. I mean, we could have just added this up, but this is fine. Let's just start with 1. So if you see for 10 to the 5th, there's not that many numbers. It's just 30 or something. So the whole point of this is like, you can actually just try every single anagram size. You can also make this a little bit better, I think. So you can even eliminate more anagrams. I didn't do this, but what you can do is you can get a count of every letter in the whole word. And then let's say your anagram size is length 8 or something, and your word is length, like what's a factor of 8? I guess like 160. That means you have 20 anagrams. So if you have 20 anagrams, that means that every letter in the anagram has to appear, like every letter in the word has to appear at least once, because every anagram uses like the same letters. So every letter has to appear at least once, and also the number of each letter has to be a multiple of 20. Because if there's 20 anagrams, every letter has to appear, you know, from some count like 1 to whatever, and there's 20 anagrams. So you can just check, so you can eliminate a bunch of anagrams that way, where you can just try all the numbers, and if it's not a factor, continue. And also you can go through all of your letters in your whole word and just check like every single letter has to be divisible by how many anagrams you have in the whole word, which is just the length of the word divided by the length of the anagram. So I didn't really do that, but this still works. So essentially I just get a letter count for whatever anagram size I pick, and then I go through the rest of the string. So if the anagram is like 20, let's say, I'll go through the first 20 characters, get a letter count, then go through the next 20 characters, get a letter count compared to the first one. And if they're different, then you can just break out of there and try a different anagram size. And you basically just go through the whole word for whatever anagram size you picked, and all the letter count dictionaries have to be equal. There's probably some better way of doing it, but this worked for me. And the first one that works, you just return true, because I'm just doing from 1 to the length of the word. So I'm trying the smallest one first. So the first one that works is going to be the smallest. And so this ended up working for me. So the last one's kind of hard, but there's an O-Ven solution, and I recognize there's an O-Ven solution, which is pretty good. There's basically just like one hard part. The rest of it is like not so bad. So you're given an integer array nums and two integers cost 1 and cost 2, and you're allowed to perform any of the following operations. Choose an index and increment that number by 1 for a cost 1, or choose two indices and increment them both by 1 for a cost 2. Return the minimum cost required to make all elements equal, and just return it the modulo of this, which is like pretty irrelevant because I'm not going to show you like a DP solution. I'm just going to show you basically an O-Ven solution, and the only reason it's O-Ven because you need like a min and a max. So in this first example, all you can really do with two numbers is just make the smaller number equal to the bigger number. You can't really use cost 2 ever, because you'll just make them both bigger, so they'll never be equal. So you just have to make the smaller number equal to the bigger number, which is just 3 times 5, which is 15. In this example, so you can say like, okay, I'll turn these 3's into a 5, and I can use cost 2 twice for that, so this will be 2. Then I can do 2 more to make this 3 into a 5 and this 2 into a 4, and then I'll use cost 1 time, which will be 2. So 2 plus 2 plus 2 is 6. And in the third example, I can just use, let's see. So I could use cost 2 and turn these into a 5. I would use cost 2 twice, which would cost me 6. Or I could use cost 1 on each of these, so that would just be 4. So there's like a bunch of different criteria for this, but I'll kind of go over all of them. So number 1 is kind of easy. It's just if cost 1 is less than or equal to cost 2 over 2. Essentially just saying like if cost 1 is cheaper than cost 2 or the same, you can just do cost 1 on everything and just turn everything. Like the goal for the most part is to turn everything into the biggest number, right? So you just be like, okay, how many operations do I need to turn every number into the biggest number? And you can get that in O-Ven. So like this would be, 2, this would be 2, this would be 2, this would be 3, and so on. And you just add all that up, and then you multiply it by cost 1. So that's pretty easy. Number 2, just try to use cost 2 always, then cost 1 if there's something left. Now, how do you know if there's something left? So basically, let's just make an array, like here. We'll just have some numbers. And I'm going to have them in sorted order to make it easier. So let's just say it's like 60, 50, 40, 40, and like 10. Think this will work? No, this won't work. I need to make this bigger. 45, 45. Just make this 0 actually. Okay. So essentially, one thing you could do is just, you always take the two smallest numbers and you increment them, and your goal is to try to get the 60. So you could say like, okay, I'll just take these two smaller numbers, increment them as much as I can using cost 2. So I'll make this go to 60, I'll make this go to 15. And I just use 15 operations of cost 2 here. So actually, instead of even counting how many operations, I can just calculate total operations. So I use 30 operations here, and I can either use cost 1 or cost 2 to have done this, right? Because I could either have incremented one at a time or use a pair. Okay, so now that this is 60, now I'll do the same thing here. So I will just increment this one and this one. So this will go to 30. This will go to 60. And I use 30 more operations. Or 15 cost 2s, right? Either one. Now I have one more. So I'll increment this to 60. And this will go to 40. And I have used 20 operations there. Now here, I'm stuck with this. So, and there's not really anything I could have done here. Like, because this was so small, if I use this with cost 2, there's no really any way I could have made this 60 along with something else. There's nothing I could have done. So now I'm just going to say, okay, well, fine. I'll just use cost 2 for all of these. So cost 2 is just going to be like 80 over 2 cost 2s. And then for the rest, I'll just use cost 1. And that might work. So this depends on, this is like one way to do it as well. This depends on cost 1. Right? So this is step 2. Just try to use cost 2 and then cost 1 if there's something left. And you can calculate all this and I'll show you in the code. It's not that bad. So that's basically it. You just calculate, like, once I make everything else the biggest number, how many more do I need here? And if I have enough operations to do everything else, then I can just use pairs, and then I might have like 1 left over or something, in which case that's fine for now, right? Like, for example, if this started off at like 30 and these were, you know, let's just say like this, I could have easily done it because I could do like 10 and 10, 10 and 10, 10 and 10, that'd all be 60. But because my first number was so small, I couldn't have really done anything here. So that's another way. Okay, so a third way, after we try these two, is, so our goal originally was to try to make everything be the biggest number. Now we're going to say, let's try bigger numbers. So instead of using, like, for example, let's say cost 1 is like 1,000,000 and cost 2 is 1. So we really want to use cost 2 as much as possible, and like we don't want to just use cost 1. So another way to do this is, what we can do is we can just say, okay, instead of making it 60, let's just increment these numbers, and let's increment this along with each one of these and see what happens. So let's say instead of 60, we get these to 61. So if we do 61 here, now we can do that and this in one operation. So this will be 41. Then we'll do this 61, so we can increment here again, 42, 61, 43, 61, 44. And we can basically keep doing these, and these numbers will catch up. So notice these numbers are now 17 away from each other, and they used to be 20. And basically, if you do this one operation, so of one operation of increment all numbers by 1, but increment smallest number by n minus 1, right? Because essentially we're just going to make pairs. We're going to say increment both of these, increment both of these, increment both of these, increment both of these. So what's going to happen here is all of these will get incremented by 1, and this will get incremented by n minus 1. So how much did this get closer? So this actually got n minus 2 closer, because all of these got incremented by 1, and this got incremented by n minus 1. So every time we do this operation, this number gets n minus 2, where n is like the length of the array, closer to the other one. So essentially we can figure out like how many times we need to do this. So because this is 20 away, the length of the array is 5. So how many times can we do this? Now we might not get like an exact match at the end, but how many times can we do this to get it as close as possible using this strategy? So n minus 2 equals 3, right? And we are 20 away, so we could use this operation 6 times. And then this number will only be 2 away now. So basically what will happen is if we use this operation 6 times, this will be 66, 66, 66, 66. And now this number will get incremented by 6 times 4, I believe. Yeah, so this will be 64. And you can just do that in OVA and just calculate that. So that's step 3. Try bigger numbers, and then now we're here. And then from here, we kind of do the same thing. So we say, like, let's just use cost 2 if we can, but if we have stuff left here, so in this case, we can use cost 2 for like whatever, like we can still calculate like how many operations does it take to get to this thing from our original numbers, you know, whatever our, like let's say our original numbers were like, you know, 50, 50, 50, 60 or something. Like this is basically just we already calculated how much it took to get to the previous state, and then for each one of these it actually takes, I believe it's n more, because this number gets incremented by 1 and all of these get incremented by 1. Or no, this number actually gets incremented by not 1. This number gets incremented by a lot more. But we already need to get that number up. So it's kind of like, it's kind of confusing, but if you just walk through the steps and you walk through the code, you'll see why this takes n more steps, essentially. But basically, yeah, then you just figure out kind of the same thing, like how many singles do I have left? So in this case, I have 2 singles, and then my overall total of steps to get here is either going to be odd or even. If it's even, then I can just use cost 2 the whole time. If it's odd, then I can use cost 2 almost all the time, and then 1 cost 1. But here I reduce my cost 1 to only 2. But you can actually reduce this further, and this is step 4. So step 4, depending on... so you can technically just do this, you can technically loop this just twice, and it'll work, but this is technically like depending on length of array, either try 1 number bigger or 2. And this will ensure, so right now, this is still like okay, but it's not great because we're still using cost 1 twice. But we can actually still do something further. So we can say, like, instead of making these numbers 66, because we can't really do anything here, let's make them 67. And I'll kind of show you like a way to, like one way to get these closer, but you don't really need to care how to get there. You just need to really care about the numbers that show up in the end, and I'll show you that as well. So let's say I want to make these 67. So one thing I could do is I could do the same thing, right? I could say like, okay, well, I'll make the 65, this 67. Then I'll make this 66, this 67. Now I'll make this 67 and the 67. So something like that. And then depending on if I want to have, so notice that I basically added 5 like total. Actually, let me go back. I think I might have screwed something up here. So yeah, I did. I think I probably did. So this is 66. Okay, this was 60. This should be 64. Yeah. So in a pair, I'll make the 65, the 67. I'll make this 66 and this 67. And this like this. But this is not necessarily the best thing. What you're really doing here instead is you can kind of go back to the previous numbers. So I don't think this is like accurate. I think it's better to show it like this. So like in this example, this was 2 away, but let's go back to our original numbers of, you know, let's say this is, I forgot exactly what it was. I think it was like 10, 40, maybe this wasn't the exact thing, but it's still going to be like the same thing. 50, 60. In fact, this needs to be like 0, I think. So basically, we're saying like instead of going to 65 or 66 or whatever, we're just going to take every number, make the 60. We're going to take every number and make it go to 67. And so there's a way to do that where you can basically do it in pairs as well. So we kind of start back here, but we already calculated how much it took to get here. But let's see how this will work. So to get to 67, basically we're going to kind of do the same thing. And like I said, we don't really care how to do this. It's always possible though. So, and then we'll try 68 as well. And you basically need to try like 1 or 2 more numbers because if you add an odd amount, like it might go from even to odd, which is bad because you might have like a extra operation. So you need to basically add twice. So you basically need to try 67 and 68, and then you're guaranteed to either have one of those be the result or the first one to be the result. So yeah, so if we try 67, then we could say like, okay, well, maybe we'll like make this go to 67 and we can add 27 here. And now we can go this is 67, so we can add 27 here. And now we can maybe make this go to 67. So we can add, actually, I don't know if we want to go exactly to 67. Let's say this goes to 60. This will go to 64. So we basically just want to get these like as close as possible, and now this is kind of doable, right? Like maybe you can go to like 64 and 64 together in a pair, and now you can go like 65 or 65, you know, and so on, and you can kind of just always have them like really close to each other. So like 65, 66, and then maybe like 66, 66. So something like this. Right, and now you see like we got them all to 67 using pairs, and now we only use this operation one time. But there are cases where you will need to use this thing twice, or not this thing, but like you will need to like go to a number that's too higher, and it basically depends on like what number are you at exactly, and then is your array length odd or even? Because if it's even and you increase every number by 1, you're adding an even number, but if it's odd, you might shift your number of operations from odd to even or even to odd, so you want to always make sure you keep it like even to even and so on. But this is essentially the fourth thing, is you try a number 1 or 2 bigger, you kind of do the same thing, get a total, and then figure this thing out. And you can get a number 1 or 2 bigger quickly using this, because, you know, if this was like 67 and this was like 2, we can do the whole operation of just like, let's make all of these bigger by 1 and this bigger by 4, and we can do all that in O of 1 and get numbers that are like pretty close to where we want them to be, and then just need a couple more. So this is still going to be like O of n. Hopefully that makes sense. Kind of confusing. Let's take a look at the code. Might make things easier. Okay, so we have the length of our nums, we have the max and the min, and then we have the total operations, which is just total. So the total operations is just like in the beginning, our step is just going to be let's try to make everything the max number in the array. So the total operations we need is just the max number minus every number in the array and get the sum of that. Then we calculate the singles, which is, like I said, once I make everything the big number, do I have anything left over here? Like, or it's not do I have anything left over here? It's how many more operations do I need to get this to this? So in this case, this would be 65. And total is everything combined. So, and like I said, if the array length is less than 2 or if cost 1 is cheaper, pretty easy, just always use cost 1. And then we have pairs and we have singles. So the total is a total number of operations. But like if this is 2 and this is 67 in our first attempt, we're just going to say, okay, all of these are fine and like everything here is fine, but to get this to 67, we can't pair this with anything. So we'll just pair whatever we have here. Like there'll be some number of operations that we use to get here. It might be odd or even. If it's even, we'll take it and use cost 2. And if it's odd, we'll use cost 2 and just use 1 for the odd. And then we're going to use only cost 1 to get this to this. So that's basically this. So we get a number of pairs, and then we just calculate pairs mod 2, which if the number of pairs is, so maybe pairs isn't like a fair number. Pairs is more like the total operations except for the singles. So this could still be odd. So if it's odd, we'll add 1 more cost 1, and we'll use cost 1 for every single. And then for every pair divided by 2, we'll use cost 2. Then we try the shortcut of, if our number is significantly smaller than the other ones, we're just going to do the shortcut of like this, where now we get our number pretty close to the other ones, right? It's going to be within n of the other ones, to the point of we can't do it anymore, right? So now our number will be like, whatever, 64 or something. Then that's the step here. So we just say, okay, and like I said, you can work through the math there. Basically, to do this, you're going to add n to every total, and then your singles now that you need are going to be less than n minus 2, because basically anytime you do this operation, you get n minus 2 closer. So if it was bigger than n minus 2, you could just do the operation again. Then same kind of thing, you get the pairs, and your result is minimum of this result and the other result. Finally, you have the last thing where, so technically you can just do I in range 2 because it's only 2, but if you have an odd length array, like I said, you might go from an odd number of operations to even, or even to odd, and you really don't want, this is like basically the case where it's like something like this where cost 1 is super expensive. You essentially have something like this, and then whatever number you went to, you just figure out, okay, like what is this difference? So this difference is 3. And then maybe like, well, maybe I'll try a difference of something less than that. Maybe I'll try a difference of, less. And I'll try this, whatever this biggest number was, let's try 1 or 2 bigger. And 1 or 2 bigger, basically, you can kind of figure it out. So if you have an odd length array, you can like do this. Well, actually, this is not the way to do it. Like the real way to do it is, like I said, you just say like, what's the total number of operations to get every single number here? Let's say I wanted 68 or something. What's the total number of operations to get everything here to 68? And you can just calculate that. You can just basically, to get every single number up 1 more. So you're not really trying to get, I guess you're not trying to get everything into a 68. You're trying to get everything like up 1 more number, and distribute it equally. And that's just n every time. So you can just do this like 1 or 2 more times. I thought you'd have to do it a lot more, but it's basically 1 or 2 more times depending on if your array is even or odd. So you can just play around with a few of these, and this was actually a test case I figured this out was, actually I don't have it saved. Maybe I have it saved? No, it looks like I don't. So, but yeah, essentially try this out for like 1 instead of 2, and you'll have the test case that it doesn't work for 1. But that's basically it. So you just try like a few more numbers, and then it works. So like I said, the thing that I got to pretty much on my own was I got all this, and I did recognize that that you can do this in kind of like an O of 1 fashion where, I mean, not really O of 1, you still loop through your stuff to get the max and the min, but everything else is just, you don't need like a heap or anything. So I got all of this, and then the hardest part is recognizing this section here, where like, if your numbers, I think the actual test case that I was looking at was something like this, where I was like, okay, once I get to the end, my numbers are going to end up looking like this. So like, what would you do here? Or let's say you start with this array, like what would you do here? And the basic thing is, if this was super expensive, you're basically going to try to want to go, I think you want to go up to like 62. So if you go up to 62 here, then this is doable. Because you can say like, okay, like right now, if you just stop here, like if cost 1 super expensive, that's going to be bad. But if you go to 62, you could be like, well, I'll go to 60 here and 62 here. And now I can go like 62, 62, 62, 62, and I have no odd operations. So that's kind of the reason there. And that's why you need to do it only 2 more times, because it just depends on if your array is odd or even. And in this case, it's odd, so you have to do it an even number of times, or 2 more times. And so this basically runs, so you get the min and the max, so like time is O of n now. We don't really need a sort either. Like some people sort, you don't need a sort, you just need a min and a max. And then everything else, like everything else is O of 1. So all of this is, yeah, all of this is O of 1. The only thing that takes time is getting the min and the max. And space, we don't really use anything either. So I think there is probably a solution where you do a priority queue, and basically the idea of the priority queue is you would basically just always take the 2 smallest elements and try to make them go up. But then that would be like a very hard problem, I think, if you did this with a priority queue, and it would probably barely pass, but this is pretty fast. Just when you recognize that like you don't actually need to do that, there's basically a few conditions you can try, and there's like 3 or 4, and most of them are pretty simple. The only hard one is, like I said, this thing where you have numbers that are kind of close to each other, like, oh, how do I do that? And you basically just increase the number you go to by a little bit. I think even if you didn't figure out that you can increase it by a little bit, you could probably recognize that I only need to increase it up to n, and I think that would still pass. So basically you could say like, this needs to get increased up to n. So whatever your number is here, like let's say it's 62 or whatever, if your array, like your array length can only be like 10 to the 5th. So you would just loop from like 62 to like 62 plus 10 to the 5th and try to increase everything to that, and you can do that. Like you can calculate the number of operations in O1 and you just loop through this, and that would basically be O of n as well. So I think this would work. But yeah, you can recognize it's only 2. Yeah. So but if you didn't, this would totally work if you just loop to this much. Because you know that if it was more than that, then this would just divide again. So it can never be bigger than n minus 2. So you could basically loop to like n minus 2 and try every single number, like your maximum plus that. Yeah, so hopefully that was helpful. And yeah, this does work pretty fast. Let's see, I think we talked about runtime and all that for all these. I guess we didn't talk about this one. So this one, so essentially you have all the factors of a number, and I don't really know. I'm gonna say it's like log n or something like that. And then so you do have to compare dictionaries for every single anagram. So I think that's like 26. So I think it's like log n times 26 times n, something like that. Like I said, you can make this a little faster. So I think this like barely, well, it should barely pass, but I think in practice like a lot of stuff cancels, so you never really get to the worst case stuff. Space though, it's pretty small because you just have a counter. So this is like O of 26, which is fine. Yeah. So, and then let's see. This one, so you're basically cutting your string into a dictionary. So this is going to be time of n. Yeah, so looping through the string and make the whole string is O of n, and space is O of n because you're basically just cutting your string into a dictionary and storing the whole thing. So I think it's something like this. And this valid word thing, depending on how you code it, it's like time O of n space O1, I think. I don't think you store, you store this thing, which is O1. Yeah. But yeah, that's going to be all for this one. Hopefully it was helpful. If it was, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.